Simply because the idea in section 6.2 is a continuation of what we learned in 6.1. So in 6.1 we talked about momentum itself, and then we talked about this momentum impulse theory. Now we're going to take that idea and just go back to momentum but conservation. So the idea that momentum can't be created or destroyed. And a good example of this, okay, would be imagine two players on a football field that were the exact same weight and they ran at each other with the exact same velocity. What would happen when they collided?
They would just hurt and fall.
Yeah, they didn't gotta stop or fall or just right there, right?
Yeah.
They would be like equal and opposite of each other. Okay? So the idea is that momentum itself can be changed or transferred, but not created or destroyed. Like a pool ball in pool or billiards. You shoot the cue ball, it hits the 7 ball, and suddenly the cue ball stops. What happens to the 7 ball? It keeps going or it moves. So you have a complete transfer of momentum from the cue ball to the 7 ball.
So when you have this transfer, what happens? What does the momentum become? Like this big, you know how
Sure, it's not a different type of momentum, it's a different object's momentum. It's just transfer from one to the other. It's not like potential to kinetic. Okay, it's just a change in the objects, not the type of momentum. So we'll use what's called the conservation of momentum theory, or the law, to determine the motion of objects here. This is simply what I was just saying a second ago. That the momentum before an interaction is the same as the momentum after an interaction. So a soccer ball is coasting and hits another soccer ball, causing that one to move. Well, the momentum before the collision equals the momentum after the collision. Right? Or instead of collision, you could use the word explosion. So think about like a grenade. The way a grenade works is a grenade explodes and pieces of it fly off in every direction. Called shrapnel. And each piece has a certain momentum in a given direction, which is then balanced by another piece. And there's a conservation of all those pieces of the grenade itself. Now, we are going to look at 2 objects only, not like 3, 4, or 5 objects. We're going to look at one-dimensional. So this is really simplified, I'm going to tell you now. Real momentum collisions involve more than one dimension, more than 2 objects. So we're looking at one-dimensional. So objects colliding like this, back and forth. Okay, it's rather basic to give you a realistic approach to this. Let's look at a first example to see this. So a hockey player swings his hockey stick. The hockey stick has a mass of 1 kilogram at a hockey puck with a mass of only 125 grams. He swings the stick with a velocity of 40 meters per second. Now think about this. How many people have played baseball or hockey or like a sport where you have some sort of a collision of an object you're swinging? Well, you might not know, okay, polo, anything, tennis. What you might not notice is that after your object hits the projectile, it slows down. It might not be noticeable, but you swing a baseball bat with a given velocity. When you connect with the ball, it slows down. So the velocity of the hockey stick after the collision is only 30 meters per second, but before it was 40 meters per second. It's because there's a transfer of some of the momentum in the hockey stick into the hockey puck. So you see the decreasing velocity of the hockey stick after the collision. Where does it go? It goes into the puck. It's what causes the puck to accelerate and then move with a given velocity after that collision. Okay? The collision takes place during a given time interval, and then after the collision, it has a given velocity. So, we think about it. Let's call M1 the hockey stick. Let's call M2 the hockey puck. What is the velocity of the hockey puck before the collision? The hockey puck? 0. So I'm calling that V2I. Subscripts are huge in these problems. Okay? 1 and 2 stand for object 1 and object 2. I and F stand for before, meaning initial, and after, meaning final, the interaction that's occurring. What's the velocity of the hockey stick initially. And after? 30. Oops. V1F. Should be a 3-0. Come on. There it is. Now, what are we trying to find? Yeah, the puck after the collision. So V2F is the question mark. Hey, let's pause here. Well, if we look at this, and we look at the momentum beforehand, we could use that equation that we wrote down. Okay, this was the one that we had for two objects. This is really telling me the following. The momentum of object 1 beforehand plus the momentum of object 2 beforehand equals the momentum of object 1 after plus the momentum of object 2 after. That's really what conservation tells me for momentum. There's no need for potential, kinetic, and everything to decipher it. Just before equals after. So you can list them. But we know that the puck has no momentum beforehand. So this is really 0 here. And then afterward, they both have momentum. The subscripts get annoying, so make sure you have the right subscripts written down. What is our goal? What are we trying to figure out? What variable are we trying to solve for? V2F. That's the final velocity of the puck, or the velocity after the collision. After the collision. Final means after the collision or interaction. Initial means before. Sure, the puck is going to continue sliding. After you hit the hockey stick, it's going to move on for a while. But this V2F is the velocity of the puck after the collision, right after. Okay, so it's going to slow down eventually and come to rest, but all we're concerned with here is the velocity of the puck as it leaves the hockey stick. Okay, as it leaves the hockey stick. So if we're solving for V2F, you can do one of two things. You can plug in numbers, or you can solve algebraically. For the first example, I'll solve with numbers. Okay, because it does get a little confusing. So we've got 1 kilogram times 40 meters per second plus 0, obviously doesn't affect it. 1 kilogram times 30 meters per second plus the hockey puck times your V2F. Subtracting 30 from 40 gives us 10. And dividing by an eighth into 10 should give you 80. Okay, 0.125, it's a common decimal, so 1/8. Divide 10 by 1/8, you get 80 as a result. Explain to me why this answer first makes sense. Why does 80 make sense as an answer?
Well, you're taking away momentum from the hockey stick, but then you also have to account for it's a much smaller mass.
Yeah.
It's a lot faster.
So, what was the change in velocity of the hockey stick? What was the change in the hockey stick's velocity? -10 or 10 meters per second loss of velocity. So, this object needs to gain at least 10 meters per second of velocity. But what's the proportion of their masses? What did I tell you? What's 0.125 really? An eighth, isn't it? Isn't this 8 times more than the velocity of the hockey stick gained or lost? It makes sense logically. Again, the mass of the puck is an eighth of that of the stick. So it gained velocity that's 8 times what the velocity of the stick lost. Alright, so make sense of your answers before you move on to the next thing. Example 2. Read it to yourself. Try and list your givens, please. Read example 2 on your own. Try and list your givens and maybe draw yourself a little diagram. So before the collision, we've got this first soccer ball, it's kicked downfield, it bumps into another one, the other one is at rest initially. Then afterward, the ball that was kicked downfield, its velocity decreases dramatically after the collision, and it goes somewhere, and we're trying to find out V2F. Take a guess, what's the answer you think? Take a guess. Why do you think it's 8?
Because they have the same mass, so you don't have to transfer the change, and then you always have to subtract 12 times 2.
Yeah, very good, Ed. Good intuition. Well done. Think about this. This kind of a problem would be like a multiple choice or a short answer. The masses are identical. So in the problem, when we have mv plus mv equals mv plus mv, what are all the m's going to be? Or,
1.
yeah, or cancel or 1 or whatever you want to call them. But the masses are identical. So this problem is actually a lot easier than it looks. But let's prove mathematically that we're right. So before the collision, the first object, mass 1, has an initial velocity. The second object is not moving. After the collision, the first object is moving, and the second object is moving. Now, what you notice is that instead of calling these M1 and M2, technically speaking, you could just call them all M. Call them all M because they're the same. The 0 has no effect on the problem because you're adding 0. So notice, every term has M in it, and that's where Ed was mentioning that they drop off. The mass is in all 3 terms. So as a result, you get V1I equals V1F plus V2F. Well, this is 12, this is 4, and this is unknown, and it's easy to do simple math. It must be 8. Okay, 4 plus 8 is what gives you 12. So this is a problem where the momenta, or the momentum, from one object is partially transferred into the other object, but its velocity, right, its velocity that's changed is identical, because the masses are identical. Different from the last example, where we had a hockey stick and a hockey puck, and they were different masses. So the hockey stick lost 10 meters per second in velocity, and the puck gained 80. Here, this soccer ball loses 8 meters per second. It all goes into the second soccer ball. There's no loss in energy. There's no change in, or there's no different mass in this part. All right? Stay with me. So, example 3. Where did I got through example 4 in the other class. Let's see how we can do. Example 3 says a person with a mass. Oh, this is a good one. All right, I'll give you a little demo. Anybody want to come up and demonstrate? Oh, I forgot. I made. Back to this. So, let's do an example. So, for example, here in this problem, we've got a person. We've got a person with a mass, focus, of 50 kilograms. This person jumps off of a ledge of some sort, a platform, maybe a dock, and they land in a boat. What would happen to the person in the boat? Yeah, we start moving a little bit, right? So, imagine now, please don't try this at home. Well, it should be kind of a cool project. If you try this at home, be very careful if you try this at home. Maybe extra credit, it's not that big. I gotta think about it, because I'm ready to test it. So imagine this is a shopping cart. That's what I'm saying, don't try it at home. And you were to just run up to a shopping cart. You ever jump on the back of a shopping cart? And roll with it? I've done this before in my parking lots. The careful part is it can flip up. That's what I'm going to say, be careful. But if you run, you just jump on, you move together, right? Okay? Now, the velocity of the cart initially is 0. I have all the momentum initially, right? Then I jump into the cart. What happens though when I'm in the cart and we're moving like this? What happens?
You add to the
It's a little bit tricky.
Well, it has wheels, so wouldn't your velocity increase?
It wouldn't increase, no.
So with you like your mass add to the chair, and then your velocity is becoming the chair. It's like becoming the chair's velocity.
Yeah, you're absolutely right. That's exactly right, Paul. You jump into the chair, and together you now have like one mass. It's called a lumped mass, right? The mass would be like m1 plus m2. And together, you and the chair, or you and the cart, move as one object, as one entity. So as a result, if you're moving as one object or one entity, you can only have one final velocity in this kind of a problem. So let's go ahead and list what we know then as a result. So my mass running is 50 kilograms. The mass of the cart was 20 kilograms. My initial velocity, notice I ran this way by the way, it was west, right? So negative V1I is negative 5 meters per second. V2I is the cart, it's not moving, so I'm good there. But now I have a lumped mass, so I'm only looking for what? But they're together. So just call it what? VF. Not VI, VF, right? It's at the end. So our goal is really to figure out VF. Remember, you have the up. You have the initial velocity of the person. You have the initial velocity of the cart, which is really at rest. This is you and the cart together rolling down the block together afterwards. Okay? I could definitely make this into an extra credit. Remind me this week. I'll give you a little tidbit of what I want you to do for this. But you need to be very careful when you do something like this. Okay? Don't like jump on the end of a shopping cart and flip up and smack your head or something, you know? No. All right, so we want to find VF before the collision. Remember, momentum before equals momentum after. The momentum beforehand is due to me, not the cart, but me. So M1 V1I. The cart has no momentum beforehand, so plus 0. And that equals the momentum after. But again, after you land in the cart, you're like one object. So how do I write the mass there? So variably? Yeah. This is the mass afterward times the velocity afterward. Again, in this kind of a problem, the objects are linked together, or they are lumped, or coupled, or whatever word you want to use, but they're locked together as one mass. So the sum of those masses is right here. The velocity is what you're looking for, those two masses together. Alright, so let's go ahead and solve for VF. Solve for VF, please. Algebraically or numerically. I'm going to divide by the quantity M1 plus M2, because that's my coefficient. The 0 has no effect on the problem, as always. We can drop that off right there, cross it out. So my result is M1 V1I over the quantity M1 plus M2. Again, you need parentheses around your denominator if you're going to type it right into your calculator. I can't emphasize that enough. It happens all the time. I keep seeing it on your tests. So I've got mass 1 times negative 5, which was the initial velocity, over mass 1 plus mass 2. What kind of an answer must you get? What kind of an answer? Negative, because I was running negative, I jumped onto the cart, and I continued to move in the negative direction. Before you give me an answer, will the answer be less than my initial velocity I ran with, or more than? Why less? Why less?
Because it's more mass, so it's moving slower.
Yeah, think about inertia. Remember inertia. The more massive an object is, the more it doesn't want to move or wants to continue to move. Well, the cart is not moving. It doesn't want to move. So part of my momentum gets it to just keep moving. And together, me and the car now are much more massive than me alone. So your answer should be less than, magnitude-wise, right? Less than 5 meters per second. What do you get? Negative? Good. Negative 3.57 or negative 3.6 meters per second. Okay, so I lost about 1.5 meters per second because I jumped and landed in the cart. See, the reason I'm trying to figure out for extra credit, by the way, is how are you going to measure this? Right, how are you going to measure velocity if you do it in a video? Like, you can do it yourself, you can actually act it out, but I want it to be realistic or something that you can actually learn from. How are you going to measure VF? How are you going to measure VI? I got to think about it. I'm trying to come up with a way to make it work. All right, last problem I want to do, then I'll give you some time, and we'll definitely do some time for homework so you can get started instead of that worksheet. Ooh, actually, are you going to do that right now? Just bring, I'm going to move. I need a chair. All right, so this may not be too reasonable, but let's try it. Can I get 2 volunteers? 2 volunteers. Victoria, come on up. Somebody else, come on.
Come on, Daddy.
Mike, perfect, come on, Mike. All right. All right, so. If, yep, actually you guys can kneel facing each other. So you want to kneel on the chair and face each other. Yep. I know. You have to hold hands, so get ready for it. Now, not hold hands, we have to push off. So if the 2 of them are ice skaters, then they're on an ice rink. And I can't simulate ice, so we'll use wheels, okay? So the ice skaters are standing together, maybe they're, just standing next to each other, and Mike says something that it said Victoria, and she's like, oh, Mike, and she pushes him like that. What would happen to Mike on ice? Sorry. What would happen to Mike on ice? He start to slide, right? So we're going to simulate this and get the idea of what would happen. So they're both not moving, right? So put your hands together like this. Okay? Do you want to actually get on a chair?
Like both?
Yeah, both these on. Come closer to here so that come all the way up. There you go, all right? Now, be careful though as you're doing it. Push off each other, go ahead. Okay, now, one thing you'll notice, depending on people's masses, depending on how much they push with, one move more than the other, right? Now, let's exaggerate, you guys are about the same size. Let's exaggerate and say, okay, I'm sorry. All right, Mike is much bigger than Victoria, okay? So, clearly, Mike can move much less. You gotta push a little harder. Let's try this one more time. Okay, let's do it again. So, okay, so Victoria weighs much less than Mike. So since she weighs much less, she's going to move much faster, obviously. So they push each other, go ahead. And look how much further Victoria goes than Mike. The idea, though, is that if you have different masses, right, when you push apart, the one with less mass is going to go much faster. You'd be like a giant taking like somebody small and pushing, they'd fly. Whereas the giant wouldn't move much. Think about recoil. If you've ever played like paintball, or if you actually carefully have been like to a shooting range and your family shoots guns, a gun has recoil on it. So the gun actually moves back, it kicks back a little bit. It's the same idea. The objects are both at rest, and then suddenly they're both pushing apart. The bullet is very little mass, right? Doesn't the bullet travel really fast? But the gun and you holding it is very massive. It doesn't kick back as much, or not nearly as fast as the bullet, or else you're hitting the face. Okay? So the idea is that massive objects move differently depending on their masses. Thanks, guys. Awesome. You can just leave it here. So let's go to this problem now. So we have 2 ice skaters that are standing together and they're at rest. They push apart. One of them has a mass of 60 kilograms, the other has a mass of 40. And the velocity of the 40 kilogram person is 7 meters per second afterward. What's the velocity of the other person? So I call them A and B here. A, B, 1, 2, it's the same thing. So, Object 1, let's say, is 60 kilograms. Object 2 is 40 kilograms. What are their velocities before the interaction?
0.
Both of them, right?
Yeah.
Again, they're at rest together. Therefore, V1I is 0 and V2I is also 0. That's the big key here in this problem. We know the velocity of person B, the second person afterward, is 7 meters per second. And we're trying to find the velocity of person A, or person 1. Now, before I go into the answer, give me something you know based on the numbers without doing any math. What's some information you can tell me? Look at what's going on, try and come up with, there's 2 conclusions you can draw, at most, right now. What's one of them? What's one of them? Ian?
Well, person A is going to go further, right?
Why is that?
Because bigger mass.
Bigger mass means they're going to go,
Oh, less distance, right?
yeah, or less velocity. Good. So less distance. Again, you're more massive. Inertia tells you that you want to stay there more. Remember, more mass is more inertia. Okay, inertia is a measurement of your, or mass is a measurement of your inertia, the desire to stay where you are. What's the second thing you could say? So V1F will definitely be less than V2F. I can tell you that because again, M1 is bigger than M2. What else? Something that's a lot more obvious as far as we picked up on it.
Velocity positive.
So the velocity would be, what would it be? Negative. Right? You push off. If you push off, which way does one person go? And the other person has to go the other way, right? So the answer we get from V1F, that would be negative, and it should be less than 7, magnitude-wise. Okay? So let's go ahead and take a look at this. We know from our law of conservation that momentum before equals momentum after. What's the momentum before, though? 0. The momentum before is definitely 0 because no one's moving. Both skaters are standing at rest. No one is moving in this problem, so it's definitely going to be 0 for momentum before. Now, what about afterward? Afterward, I plug in what I know, right? I've got M1 V1F plus M2 V2F. I know these numbers I could solve analytically for V1F, or I can just plug in. Okay, so solve 280 or negative 280 over 60. Yeah, negative 4.7 meters per second. And that validates what we said a minute ago. The fact that V2F was 7, this should be less than 7 in magnitude, and we got 4.7, clearly less than 7. Okay, clearly less than 7. Questions so far? Does the theory also make sense? Because that's really what's important here. I mean, the mathematics, obviously, you can practice, but the theory you have to understand. So do you understand why it's less velocity? It's like the David and Goliath, even though it's not really, but imagine those two, like size-wise, pushing each other. You know, David would get launched, Goliath probably wouldn't even move. Okay, much more massive moves with less velocity after an interaction. It's also got to be negative because they're pushing apart from each other. Those are those two conceptual ideas in this problem. All right, or Jake.
The conductor is carrying 1,000 kilogram steel beam while cruising at a velocity of 25 meters per second. The beam falls out of the back of the truck at a velocity of 18 meters per second, and as a result, the truck accelerates to a velocity of 30 meters per second. Determine the mass of the truck.
All right, so think about it physically. The iPad is the truck. My stylus is the beam. The beam is sitting in the flatbed in the back of the truck. Imagine the tailgate falls down, so the beam is no longer supported, and suddenly the beam slips because there's very little friction. So here's the truck. The beam, which weighs a lot, like a metal beam that's almost 2,000 pounds, that's a good weight for that, slides out the back of the truck. So now suddenly the truck doesn't have to pull the beam too, so it speeds up. The same amount of gas on the accelerator, suddenly the car accelerates from 25 miles an hour to 30 miles an hour. And think about that logically. If you're carrying somebody on your back, imagine like your younger brother or sister, right? You're walking with them on your back and they jump off. It's a lot easier to move without someone on your back. That's the same thing as the truck here. You apply a certain amount of force on the accelerator, as soon as that beam is no longer in the truck, it's going to have significantly less mass to pull, and therefore it's going to accelerate automatically. So let's think about this problem, and let's use the context of the problem to help us write the equation. First, the overall equation we're always going to use with momentum. When you only have mass and velocity, that's your key point here. There's no force or time. Okay, you're going to use this one to start. Okay, that's always going to be the formula you're going to use for conservation of momentum. Remember, the other formula is delta P equals Ft. There's nothing about impulse in this problem. There's nothing given about force. There's nothing given about time. So there's no reason to even use that one. Now, what does Pi mean? Pi. Say again? Yeah, the initial momentum. Whether there's 1, 2, 3, 4 objects, you have that many parts to it. How many objects do we have here? You have 2 objects, right? You have 2 objects. Each of them have their own masses. Each of them have their own velocities. Now, in the beginning of the problem, remember, here's the truck, here's the beam. They're moving together. And then it slips out the back, and it's still moving, but it's trailing, hits the ground, and the truck keeps going. So that's why it still moves at 18 meters per second. But when they're moving together, what could you say? Their velocities are the same. So VI is the same for both the truck and the beam. It's 25. Again, here's your VI. It's 25. It's the same for both of them. They're moving as one entity. So beforehand, instead of writing this, please don't write this. Instead of writing M1 V1I, V1I plus M2 V2I, what could you do instead of writing them separately?
M1 plus M2 and M6 times VI.
Yeah. And just call it VI. You don't need to specify V2Y and V1I, so you don't need to do this one. So the reason I'm able to do that is because of the context of the problem. I got a question in the last class that I always seem to get. The question was, is this always the equation we're going to use? What's the answer to that?
Unlike Tom.
It's not always, thank you. Everything is going to be different. Okay? Depends on the problem itself. Now, we've been using the words explosion and collision. Other ways you can think of is like after the separation between the beam and the truck, what's happening is the next question. So, what do you want to call the beam? M1 or M2? Doesn't matter.
M2.
M2? All right. So let's say M2 is the beam. So that's 1,000 kilograms. That means we're looking for M1, right? That means we're looking for M1, which is the truck's mass. Now, on the right-hand side of this, I know that there is momentum for the truck, because it's moving on its own now, and there's momentum for the beam, because it's moving on its own now. So the way we wrote this and crossed it off, we're going to use that same exact writing, but with instead of VI, Mike? Why? Because I prompted you with that, okay. But why in the context of the problem? What is VF over here? What is this all about? The right-hand side of the equation. The final what?
Final results, final.
Okay, but what's P stand for again? Yeah, the final momentum of the system. So each individual piece of momentum needs to be accounted for. That's why when I taught you this law, I originally wrote this. Remember we put sum symbols there in the front? Those summation symbols, meaning the sum of. So after the beam slides out the truck, out the back of it, we've got the mass of the truck times the velocity of the truck after. We've got the mass of the beam times the velocity of the beam after. And And when I say after, I mean after whatever has happened. After the objects separated, after they collided, after they fused together as one object, after whatever it was that happened. That's what after is referring to here. So again, our goal is to find what?
The final velocity. Oh no, the mass of the truck.
Mass of the truck. Why does that pose a problem? Why is this harder than what we've done so far? Yeah, M1 is here, but M1 is also here. So which M1 are we solving for?
The second. This one. Both of them, because we don't know either.
Yeah, I'm hearing the same. I'm hearing this one, that one. The M1 is M1. So you need to just solve for M1 in general. It's like a variable. So if you had, think back to algebra. If you had x on one side of the equation, like 7x, on the other side you had 5 minus 2x, wouldn't you have to combine the x's, combine like terms, and then divide by the coefficient? So think of M1 as your unknown. So let's progress through this problem, and we have to combine our M1s toward the end. All right, we have to think about the fact that we're solving for M1 in general, but it appears in two spots. So it may be useful in this kind of a problem to plug in numbers. Some people like to do that at this point. I'll plug in numbers real quick, and then I'll show the algebraic solution also. Paul?
No.
Sure? Okay. So if I were to plug in numbers, what's the initial velocity, VI, of the truck beam combo? Before any separation, what was the velocity?
25.
Yeah, 25 meters per second. The mass of the truck is the beam is 1,000 kilograms. The truck is unknown. The truck is still unknown, so I still write M1. What is the velocity of the truck after the beam falls out the back of it? What is it? 30 meters per second, good. Plus the mass of the beam, which is 1,000, times the velocity of the beam, which is 18. So the beam is still moving forward. Remember, you shouldn't do this, but have you ever spit gum out the window when you're driving, or just spit out the window? What happens? Flies back, right? So it looks like it's going backwards, doesn't it? But in reality, here's what's happening. Ready? Here's you in the car. Here's the gum you're about to spit out. So here's the gum, the piece of gum. I'm trying to make a little particle. Okay, here's the car. You spit it out the window, and it looks like it shoots back, but here's really what happens. Ready? It hits some air resistance, and it still moves forward, but it doesn't move forward as fast as when it hit the ground. You keep going. So when you throw something out of the car, inertia tells us an object is in motion and wants to stay in motion. Well, it was moving forward. That's why when you see stunt devils in like movies, you see them jump out of the car and roll to a stop. It's usually not like that. If you jump out of a car that's moving at like 40 miles an hour, you will roll at 40 miles an hour until you stop from friction, until you get enough cuts and bruises and scrapes. So it's not realistic. Okay, when you throw something out like a moving object, it's still moving, but it slows down because of air resistance. So the beam is still moving forward. But because the beam was kind of sliding back in the truck, imagine this. The truck is moving at 25 miles an hour, or meters per second. The beam is sliding back at 7 meters per second. So overall, although it's moving 25, it's sliding back with 7. So 25 minus 7 gives you the 18, wherever it is, the problem that we're going to use for the velocity of the beam. So you have to think about vectors here. Okay, so yes, this is positive 18 still. It's still moving forward. The beam is not actually moving backwards here. So at this point in time, you're trying to find M1. It's in two spots. Distribute the 25, combine like terms, and let's get M1 by itself. I'll do the algebraic solution in a minute. All right, so distributing, I've got 25 M1s plus 25,000 equals 30 M1s plus 18,000. Okay, it's just algebra at this point. 25x, 30x, 25,000, 18,000. Okay, combine your like terms. I would personally subtract 25 M1, so M1 stays positive. And at the same time, I would subtract 18,000 from both sides. I would not do this in two steps. I would say my algebra skills are, strong enough that I can do this all in one step. 25,000 minus 18,000 gives you 7,000. 25m1 minus 25m1 drops off. And on the right-hand side, 30m1 minus 25m1 is 5m1s. And 18,000 minus 18,000 obviously drops off. So then just divide by 5. You're going to get, yeah, there it is. 1,400 kilograms is the mass of the truck. So clearly the truck weighs more than the beam here, but not that much more. Okay, a metal beam can weigh up to thousands, many thousands of pounds. It can be much more massive than the truck. And then you would probably use more of an 18-wheeler with a big flatbed that you'd put all the beams on. Okay, they'd be strapped down. They wouldn't even really have to be strapped down because they're so heavy that there's so much normal force, right? There's so much weight pushing down that there's so much normal force, the friction is so high in a problem like this. Okay? Now, let's take the original up here at the top, though, real quick. Okay, if you want to watch, you can watch, or you can write it. And let's solve this algebraically at the bottom here. All right, so I would do the same thing. I would distribute VI. Remember how I distributed the 25 right here to both? Distribute the VI to both of these. You're going to get M1 VI plus M2 VI equals M1 V1F plus M2 V2F. Again, I'm taking the line up at the top there, distributing the VI in red. So that's what I get at the bottom now. And if I wanted to solve this algebraically, I need to get M2 on the same side. So move this over here by subtracting it. Move this over here by subtracting it. So this becomes M1 VI that remains. Then I take this M1 V1F and subtract it. So minus M1 V1F. Then on the right-hand side, I've still got M2 V2F. But I need to subtract M2 VI over here. And if you haven't by now, please pick up on the fact that when you add or subtract something from side to side, you just change the sign. That's all you're really doing. See how this became negative here? This here became negative. Those are negatives because they were originally positives. Now what can I do on the right-hand side? Why did I move that over? What does that allow me to do on the right-hand side of the equation? Remember the goal of the problem. Remember the goal of what you're trying to do. What's the goal? What's the goal?
Solve for M1.
So, is M1 in our problem? Sorry. Was it M1 or M2? So M1. So I should have said left-hand side, sorry. So what can I do on the left-hand side if my goal is to solve for M1? Right, M1 is in both, I did M2 in the class, that's why I'm mixing the numbers up. So we're looking for the mass of the truck, M1, and it's in both of these spots. M1 is in both spots. I can't solve for M1 here by itself, I can't get M1 here by itself, but if it's in both terms, what can I do? Not cancel, use another word. What's the word? Not take them out, sure, but mathematically. What is it? GCF. What does F stand for? Factor them out. So, ready? Factor out M1 because it's a GCF here. And you get VI minus V1F left. The right-hand side, leave alone. Again, in case you're wondering when you factor something out, if you forget what's left over, like how do you know this is left over right here? Just take this, divide it by whatever you factored out. If you divide this by this, you're just left with VI. Divide this whole thing by M1. You're left with negative V1F. Negative V1F. Okay, and then how do I get M1 by itself? Last step. How do I get M1 by itself? Divide by? Very good. Okay, and those cancel, and that's M1. So if you go ahead and plug into this expression right here, this is the exact same answer. You'll get 1,400 kilograms plugging in here. The reason I tell you in this topic to plug in earlier if you'd like to is because the subscripts get very, very tricky. And it's easy to make little mistakes along the way. So if you'd like to and you want to plug into these kinds of problems, please, by all means, plug in. Okay? There's not really a necessity to solve algebraically here. Now, when you work on your worksheet in a minute, you're going to see that when you solve these, you get repeated similar solutions, though. So sometimes solving algebraically is nice to see what the solution looks like. But feel free to plug in. Okay? So solving this, you're going to still get 1,400 kilograms.